Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on basic control systems for mechanical engineers. In the last lecture we discussed about stability. Today we are going to focus on PID control. So let us start with a simple control system diagram. So this is a common negative feedback system. And this is the error and this is the control input U, R is the reference, Y is the output, D is the controller, G is our plant. And the error is given by 1 plus G into D times R. So let us describe this whole thing as some S. So basically the error is S times the reference R. Now the most common type of R you will find at least in time domain is in the polynomial form. So let us take R of t to be t to the power k divided by k factorial, and this is into 1 of t. This 1 of t represents that it will be 1 when t is greater than 0 and 0 when t is less than 0. So based for this particular R of t, if we look at the Laplace transform table, we get R of s to be 1 divided by s plus k. So this transfer function is valid for a polynomial reference. So the error, basically the steady state error, can be given by the final value theorem, is limit s tends to 0, s e of s is basically limit s tends to 0 s times. So we are going to insert this equation here. So we will get 1 plus gd and into r. Now we know we are then going to insert this particular value of r here. So we get s 1 plus gd divided by 1 by s to the power k plus 1. So this is our expression for the steady state error. Now in this expression, let us consider that if k is equal to 0, what happens? If k is equal to 0, the steady state error will be limit s tends to 0, s times 1 divided by 1 plus gd divided by s. So this cancel out, and what we are left with is limit s tends to 0, 1 divided by 1 plus gd, and say this gd as this limit s tends to 0, this gd of s is basically gd, instead of s we put s is equal to 0. So let us denote that by definition to be some kp. In that case ESS is equal to 1 by 1 plus Kp, and this Kp is basically a error constant. And this kind of a system is called a type 0 system. So this type of a case is called the type 0 case with respect to the reference trajectory r. Now let us consider that this G D, basically G into D of S can be expressed as G D sum G D O of S divided by S to the power n. Here n is a system characteristic, and what we have seen so far, K is a characteristic of the reference. So now if we substitute this in an expression for ESS, we get, instead of 1 plus GD of S, we will substitute 1 GD0 S divided by S to the power n, and here we have 1 divided by S to the power K plus 1. So we could, based on this, if we denote this GD0 at value S is equal to 0 as some Kn, then we can write the error, that is steady state error, as limit S tends to 0, 1 divided by 1 plus Kn by S to the power n, and this S here will cancel out with one of the S here. So we have 1 divided by S to the power k. Now we can rearrange this to get the equation S to the power n divided by S to the power n plus k. Once this is done, now we have S to the power n and S to the power k, and depending on the relation between n and k, that is the system characteristic and the reference characteristic, we will get different scenarios. So say we say if n is greater than k, in this scenario what will happen is, if n is greater than k, then we will have here S to the power n minus k, and the power will be positive. So this will go to 0. So we will have ESS is equal to 0. In the scenario where k is greater than n, then this particular part will dominate. In that case, we have that the steady state error will tend to infinity. Now if n is equal to k and both of them are equal to 0, in that scenario S to the power n and S to the power k will be equal to 1. So what we will have, the steady state error is basically 1 by 1 plus k0. And if n is equal to k and they are both not equal to 0, then in that scenario what we will get is, it will be 1 divided by kn, where k0, kn are error constants. So based on this, we can formulate basically a table such that, here let us consider the different types of input. So k is equal to 0 basically represents a step signal, k is equal to 1 represents a ramp, reference k is equal to 2 basically represents a parabola. Similarly, on the other side, if we look at the scenario where n is equal to 0, that is a type 0 case, then we will have n is equal to 1, that is type 1, and n is equal to 2, type 2. So, now if we consider n is equal to 0 and k is equal to 0, we have this particular scenario. So, we have 1 divided by 1 plus kp, where kp is an error constant. In the scenario where n is equal to 0 and k is equal to 1, this will go to infinity, and the same holds here, this goes to infinity. This scenario where n is equal to 1 and k is equal to 0, this is equal to 0. Then for a n is equal to 1, k is equal to 1, we have 1 divided by kv, and this goes to infinity. Here we will get 0, similarly here we will get 0, and this is 1 divided by some error constant. Now these error constants kp, kv and ka can be defined in terms of our system. So, kp is basically as s tends to 0, g times d of s. Similarly, kv is limit s tends to 0, s times g d of s, and ka is limit s tends to 0, s g d s square times g d of s. Now here for simplification of notation, we have just considered s only in d, but it is basically acting on both. So, it is g of s into d of s. So, these are the error constants. As you can see, this is a position error constant, this is the velocity, and this is the acceleration constant. So, what does this whole thing tell us about? So, for example, say our we have a step input and we are giving it to a type 0 system. So, by type 0 we mean that the transfer function will have g into d0 divided by s. So, basically one pole at the origin, there is s to the power 0. So, that means there is no poles at the origin. So, that represents a type 0 system. So, in that scenario, if a type 0 system is tracking a step input, basic step reference, then we will have the error will be 1 divided by 1 plus kp, and kp is given by this expression. Now, if we have a type 1 system where the open loop transfer function gd has one pole at the origin, and we are trying to track a step, then we will come to this entry, that means the error will be 0. The steady state error is basically 0. The same applies for the step input, and if we have two poles at the origin for the open loop transfer function, we get the steady state error to be 0. Now, if we take a ramp input and we apply to a closed loop system which has an open loop part gd of s with no poles at the origin, then in that scenario our steady state error will go to infinity. So, this knowledge, this table is where helps us to understand for any given polynomial step reference such as step, ramp or parabola, which systems give us 0 steady state error, what type of a system will give us a 0 steady state error, what type of system will give us an steady state error which tends to infinity, or we will get some constant, and what is the value of that constant. So far we have understood this table and how given a parabolic input, given a polynomial reference input, what kind of a system will give us which kind of an error. Now what we will do is we will consider a few examples. So let us consider G of S to be a simple first order system, that is there is just one pole, and D of S to be some constant k. So if we multiply G into D, basically we get A k divided by tau S plus 1. In this scenario, for the closed loop system, this will represent a type 0 system. That is because if we look at the open loop transfer function GD, there is only there is no basically no pole at the origin. So basically n is equal to 0, and in that case if we go to this previous table where n is equal to 0, for a step input the error constant will be Kp limit s tends to 0 Gd of s. So in that case this will be equal to A times. Now let us consider another case. We have the same system G of s, so it's A divided by tau s plus 1, but our D of s, what we are doing, instead of having just a constant k, we will have k plus ki by s. So if we look at G into D, what you will see is we will get A times ks plus ki divided by s into tau s plus 1. So now if you see this system, if you consider the open loop transfer function, you will see that there is a pole at the origin, which implies that this is a type 1 system. And in this case our error constant Kv is limit s tends to 0 s times G d of s. So in this scenario it will turn out to be A times Ki. So far we have focused on a polynomial input and reference input, and the type of the identifying the type of the system for the closed loop system based on the open loop transfer function, and what kind of a steady state error we get. Now we will next focus on a very important aspect of controls, which is PID control. So PID control means P stands for proportional, I stands for integral, and D stands for derivative. So let us draw the block diagram. So here we have the reference, the summation, we get the error, and our controller. So here we have the proportional part, next we have the integral part, and finally the derivative part. This generates U, which is sent to our plant, and this is the output Y, which is fed back to get the error. Now let us consider a scenario in which we have, so this is time, and here we'll have the reference, reference and the output. So let us consider that the reference looks something of this form. So this is basically R of t, and our corresponding output looks something like of this. So in this scenario you will see there the error will look something of this form. So based on this we can formulate. So if this is the error, first we'll consider the portion of the proportional control input. So in this scenario it will look, this will be just multiplied by some constant, so it will move upwards. So we'll get Kp into E of t. The next we'll consider the integral part, where it will start from here and go to some value. So this is integral of the error multiplied by a constant, and this represents the portion of the control input which goes to integral. And then the other case we have the derivative. Since this is a constant slope, we will just have a straight line, so we get Kd dE by dt. So this represents the derivative part. So these are the three portions of the control input. So then we'll just sum them up and we'll get the overall control. So this proportional gain, as you will see here, is just going to move the error multiplied by some constant Kp. The integral will keep on accumulating the effect of the error, as you can see in this figure. The Kd is more of an anticipatory factor, and that can also be seen by this expression Kd into S. So it kind of looks into based on the past, looks into the future. So it's an anticipatory effect, and we can combine these three to get our control input. Now the most important question is, how does this affect the performance in terms of the time domain specifications. So a few lectures back we discussed about a concept called rise time, overshoot, then settling time, and we are discussing steady state error. So now let us consider how Kp, Ki and Kd affect these important aspects. So Kp and Ki will basically reduce the rise time, because they will result in one Kp will just proportionally increase the effect of the error, trying to reduce the error, and it will move the curve upwards. Same with Ki, and for Kd we will have very small change, so it's very negligible. Now in terms of overshoot, Kp will increase basically the overshoot. The same will happen with Ki, but in case of Kd it will reduce the overshoot, and this reduction in overshoot can potentially help us increase Kp, which might be beneficial in other cases such as rise time. Now in terms of settling time, Kp has very little effect on the settling time. Ki will tend to increase the settling time because it will result in more oscillations, whereas Kd will tend to reduce the sampling time. Now coming in terms of the steady state error, Kp will basically reduce the steady state error. Ki will significantly reduce and in most cases eliminates the steady state error. That is a very important reason why we use an integral gain in the controller, and Kd will results in a very small change. So this is the effect of the different types of gains on these time domain specifications. Mostly proportional plus integral controller is used. Derivative many times might not be used. Another reason besides these leaving aside these time domain specifications could be because if we look at a control diagram, we take the output to generate the error, and this output is obtained from a sensor, and the sensor can have some noise. So in that scenario what happens is this noise will be is introduced in the error, and if there is a derivative gain, this the noise in the error can be amplified in the control input and will reach the system. So that is not desirable, and therefore sometimes this derivative gain is not used, or if the derivative gain is used, we have to add a filter. So now that we have studied this PID controller, let us consider some examples where we try to apply this type of a controller to first order and second order systems. So let us first focus on just using P control and seeing the effect. So let us consider G of S is equal to A divided by tau S plus 1. So this represents a first order system. Now we are going to consider that D of S is equal to Kp. So we get tau S plus 1 plus Kp is equal to 0 as our characteristic equation. This equation is the equation for stability, which is basically 1 plus Gd is equal to 0. So from this we get tau S plus 1 plus Kp is equal to 0. So this the root of this equation represent the poles of the closed loop system. So if we just divide by tau, we get 1 plus S plus 1 plus Kp by tau is equal to 0. Sorry, this is A times Kp. So based on this, we can see that by selecting Kp, we can change pole of closed loop system, because there is just one pole, and if we just and it will be dependent, it will be just minus of 1 plus A into Kp divided by tau, and if we just change Kp, we can change the location of the pole. Now as we have discussed in the previous lectures, becomes very important. One is from performance point of view plus the stability. So we can control the poles of this system. Now let us consider an alternate case where we have for the same proportional controller but a different system, A divided by S square plus A1S plus A2. So this represents a second order system. So now if we apply 1 plus GD is equal to 0, what we will get is basically S square plus A1S plus A2 plus capital A times Kp is equal to 0. So now based on this, if you see in this case, we have two poles of this system. So there are two roots of this equation and Kp only influences one coefficient. So we cannot place these poles as per our desired because only one coefficient is affected. Also in the scenario, so if we calculate the error constant, that's basically limit S tends to 0, since this is a basically a type 0 system, we will have G S. So in that case this error constant capital Kp will be basically be equal to Kp in the proportional gain Kp into A divided by A2. So the steady state error will be 1 divided by 1 plus capital Kp, and in that case what we get is A2 divided by A2 plus the proportional gain small Kp into A. So if we make Kp large enough, we can reduce the steady state error, but we can only control one coefficient here. Now let us consider the next example where we have a PI controller. So in this scenario, D of S is equal to small k small kp plus ki by S, and we consider the first order system G of S is equal to A divided by tau S plus 1. So if you multiply G by D and everything, you will see that this represents a type 1 system. So if we consider 1 plus GD is equal to 0, what we will get is 1 plus A divided by tau S plus 1 into Kps plus Ki divided by S is equal to 0, and in this case we get, this implies tau S square plus A Kp plus 1 times S plus A times Ki is equal to 0. So in this case we have S square, we can rearrange this just dividing by tau. So now in this case, if you see, there are two poles. So if we consider this coefficient, its value can be changed by varying Kp. Similarly here, for this coefficient we can just change the integral gain Ki to vary its value, and therefore both coefficients can be changed by varying the gains. So basically poles can be placed at desired locations. So this was a PI controller applied to a first order system. Now let us consider a second order system. So in this case, our characteristic equation will be 1 plus A divided by S square plus A1S plus A2, and this will be multiplied by KPS plus KI divided by S is equal to 0. So in this scenario, we will have SQ plus A1 S square plus A2S plus A KPS plus A times Ki is equal to 0. So we can club these two parts here with which have common S coefficient together to basically get A2 plus A times Kp into S. So here if we see there will be 3 poles and we are interested in 3 coefficients. The one corresponding to S to the power 0 can be controlled using Ki. Similarly, S to the power 1 can be controlled using Kp, but the coefficient corresponding to S square is independent of the controller gains. So we can change only these two coefficients and not this one. So we can only change two coefficients. By changing controller gains. So this PI controller might not be very ideal for this second order system. So we'll go 1 degree higher, we'll consider the full PID controller. So we apply PID controller, our D of S is equal to Kp plus Ki by S plus KdS, and G of S is the same second order system we had. So now if we take 1 plus GDS equal to 0, what we will get is we will get SQ plus A1 plus KD into A S square plus A2 plus A into Kp, this whole thing multiplied by S, and we will get A times Ki as the constant. So now in this scenario, if you see here, all the 3 coefficients can be depend on the controller gains Kp, Ki and Kd. So we can control all of these and place the poles at the locations we want. So that is what we discussed through these examples. To summarize is the selection of whether we want a P, PI or a PID controller will be dictated by the plant and what kind of reference we are dealing. So in scenario of the plant, the controllers the gains Kp, Ki and Kd can help us to locate to place the poles at certain locations in the S plane in certain scenarios, and certain cases it might not be possible. So depending on the type of system, whether it's first order or second order, we need to select whether we want a P controller, PI controller, PID controller or a PD controller to such that we can place our poles at our desired locations, and these locations of the pole will determine whether they meet the time domain specifications as we have discussed on our previous lectures. Also, at the same time, the steady state error will be also determined by how we by the type of the system. So, we need to understand what reference input we are giving to the system, as well as the type of the system, whether it is first order or second order, to determine what kind of controller we want to select. So, every controller and every type might not be applicable for all reference inputs and all types of plants, and sometimes selecting the whole PID controller might not also be necessary and might be an excess. So, we need to determine what we need to look at the system, that is the plant, as well as the reference input and the type of controller, and based on that select our type of controller. Now, we have with after these examples, one part which still remains about PID controllers is how do we select these different gains. So, that is called PID tuning. So, for that Ziegler and Nichols have presented some PID tuning methodologies, and we are going to study them next. So, for that what we do is we consider, say this is y of t. So, they have considered this kind of a system whose transfer function is a divided by tau s plus 1. So, this represents a first order system with a time delay of Td. So, this e to the power minus std represents the time delay, and if you plot y the output of this particular transfer function, it will look something of this form, where this is L is equal to the time delay Td, the amplitude is A, and the time it takes to rise is tau, and if we consider this slope here A, this tau, then we have something called the reaction rate, which is basically A by tau. So, Ziegler and Nichols have proposed two methods. The first one is basically that the output will have a decay ratio of 0.25, and that is for this the plant transfer function given by g of s, and this is the output of the plant transfer function. So, in that scenario what it is considered is, if this is t and this is y of t, that is after we have applied the controller to the plant transfer function. If this is the output and say this is equal to 1 and this is 0.25, and this scenario happens within the first time period. So, this is the objective of this so this is the objective they wanted to achieve. Sorry. So within one time period they wanted to go from 1 to 0.25, that is have a 75% decay. So the decay ratio is 0.25 by 1, that is 0.25. So this is the what I'll call the objective for the closed loop transfer function, and this is our the response of the plant, and the controller is expressed in this form. So Kp divided by Ti represents the integral gain, and Kp into Td represents the derivative gain. So based on this, they proposed a controller. Say we have a P controller, then what the optimum gains we are heuristically determined by them. So Kp is equal to 1 by Rl, where R is the reaction rate of this plant and L is the time delay. Next we have the Pi. For the Pi, Kp is equal to 0.9 by Rl and Ti is L by 0.3. And finally for PID, Kp is equal to 1.2 divided by Rl, Ti is 2L and Td is 0.5 L. So this is the optimal set of gains for these different types of controllers which were prescribed by Ziegler and Nicol with this particular objective of a decay ratio in mind. So this is one of the methods which is denoted by the decay ratio of 0.25. The other method proposed by Ziegler and Nichols is basically called the ultimate sensitivity method. So in this case, the proportional gain is increased till the system, that is the entire closed loop system is marginally stable. So we start with any system we have, and and we just take a controller which has a proportional gain, and this proportional gain is increased till the system is marginally stable. So as we had discussed in the previous class, once a system is marginally stable, its output will look something of the form. So it will be a sinusoidal wave with a constant amplitude. So basically sinusoidal waveform with constant amplitude. So if now we keep on increasing in to achieve marginally stable scenario, then what will happen is, and it will continuously oscillate with its amplitude limited by the actuator saturation. So in theory, we can take any system and keep on increasing Kp, and as we had seen in this, for this first order example, by by just changing Kp here in this, by just increasing Kp, we can keep on reducing the steady state error. But theoretically we can do that, but in practice what happens is there will be some saturation from the actuator. Say example, the maximum output which a motor can give in terms of current will be limited. So in that scenario, what will happen is this system, as we keep on increasing, will become marginally stable and its amplitude will be restricted by this actuator saturation. In such a scenario, the corresponding gain is called the ultimate gain, Ku. The corresponding period of oscillation, in this scenario, this period here, so that is the ultimate period. Let us denote that as Pu. So similar to what we had done here for different types of controller, optimum gains have been suggested. So the controller is, if we have P, the optimum gain will be 0.5 times this, the ultimate gain Ku. Similarly for Pi, Kp will be 0.45 times Ku, and Ti will be determined by the ultimate period divided by 1.2. For PID, Kp will be 0.6 times Ku, Ti will be 0.5 times Pu, and Td will be 0.125 times Pu. So these are the optimum suggested gains based on heuristics for P, Pi and PID controller. So these are the two methods by Ziegler and Nichols. So the first one is with the objective of a decay ratio of 0.25, and the next is the ultimate sensitivity method, where we keep on increasing the gain till it becomes marginally stable, and then depending on the gain and the ultimate period we find the optimum gains. And so in this lecture what we have done is we started with a closed loop control system and considered polynomial reference, and for different scenarios we identified under what conditions of the reference input and what type of a system will get zero steady state error, infinity steady state error, and a constant value of steady state error. And then we did few examples. Then we focused on PID controller, and PID controller we focused on how it will affect the rise time, overshoot, settling time and steady state error. And then we went on to do some examples with simple first order and second order system for P, Pi and PID controllers. And finally we focused on PID tuning, and we did two methods, that is one with the objective of decay ratio of 0.25, and this was applied to a simple first order system with a time delay, and the second one is the ultimate sensitivity method. So that is all for today's lecture. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I'm not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I'm also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain. They are all written using pre-existing. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.